Hello everyone, this is question number 15 and let's see what we have to solve in these questions. So in these questions it is written that a point charge is moving with a uniform velocity v equals to beta c along the positive x direction parallel to and very close to a corrugated metal sheet as shown in the figure. So this is the corrugated metal sheet which is grounded, and and a point charge is moving is parallel to the plane with velocity v equals to beta c. So now what we have to calculate here. So the wavelength of the electromagnetic radiations received by an observer along the directions of motion. So what we have to calculate here, there will be radiations of electromagnetic radiation. At this moment we don't know why there will be electromagnetic radiation, that we have to see. So if there is a radiation, then what will be the radiation's wavelength of this that will be observed by an observer along the direction of motion. So this is a very conceptual questions, and in a single questions we actually going to three different concept. And what these three concepts that are going to deployed here, these are first we'll use concept of image method. Second we'll use dipole concept of dipole radiation, and third we'll use here a relativistic Doppler effect. So it's 3-in-1 kind of situation. So let's see how to solve this problem. So first question is why there will be radiation. So for that, let me just remind you the electrostatics phenomena. Let's say we have a infinite grounded conducting plane. Say it's an infinite grounded conducting plane, and yeah, so it is grounded. Now if we place a point charge q in front of this grounded conducting plane, point charge q, let's say plus q, at a distance d, then since this plane is grounded, so there will be a negative induced charge on the plane. So in this case it's conducting there will be induced charge on the conducting plane. Why? Because of this positive charge will create an electric field, and because of this electric field that will apply force on the charge on the positive charge and negative charge on the conductor. But since it is grounded, so potential should be zero, and because of that all positive charge will goes to the ground and only negative charge will be there. So now if we according to image method, we can replace this induced charge by a point charge but in this case, since it's a plane infinite conducting plane, so in this case the induced charge, that induced charge will be exactly the same amount of real charge, but it will be opposite side. So it's plus q, the induced charge will be minus q, and distance from the plane will also be same. Like here the distance between plane and real charge is d, then the distance between image charge and the plane will also be d. So now you can see that this real charge and this image charge, they will behave like as a dipole with a dipole moment which equals to q into 2d. Q into 2d. So similar kind of phenomena also going to happen here. So in this case in these questions, the plane the metallic sheet is not plane, but it's a corrugated like this. Corrugated like this. So because of this shape, let's say if now this charge is moving parallel to the metal sheet. So at any time, let's say charge particle reaches at this position. So at this time you can see the distance between charge particle and the metal sheet is this. So because of that there will be induced charge also. Now if we want to replace this induced charge by an image charge, so according to this concept, I have to replace this induced charge by image charge, and then we can replace like this way. So this distance and this distance must be same, and if it is plus q, then here it will be minus q. Now since this charge is moving in positive x direction, real charge is moving parallel to the plane sheet and in positive x direction, so towards right direction. So later this charge particle will not be at rest at this position all the time, so it will move with time. So later time, let's say charge particle reaches at this position. Okay, so when charge particle will reach at this position, at that time we can see that this will be the distance from the metal sheet. So because of that, since this distance is less than this distance, so here image distance will also be reduced from the initial distance. So this will also be like this, with this. And consider a situation where charge particle reaches at this position where the distance is very small. It's very near to the metal sheet. So at this time, image will also be from very small distance in this image. And then later you can see that charge particle will reach here. So at that time, image charge position will be here. And later time, let's say charge particle will reach here. So at that time, the image distance will be here. So you can see here like that real charge and image charge, they will form a dipole, but in this case the charge particle was rest, and because of that the dipole was always fixed. But here you can see as the dipole is moving, charge particle is moving, so the distance between plane and the charge particle is actually decrease in a periodically manner, and because of that the dipole moment of this dipole that is generated because of real charge and the image charge, that dipole actually oscillate with time. Oscillate with time. So now we know the concept that if there is a oscillatory dipole moment, then there will be a radiation. And what will be the frequency of this radiation? The radiation frequency will be exactly the same frequency with the dipole is oscillating. So in order to calculate the frequency of the radiations, what we have to calculate first, we have to calculate the oscillations frequency of the dipole. Oscillations frequency of the dipole. Now to calculate the oscillations frequency of the dipole, let me introduce two frame of reference. One frame of reference called S prime frame, which is at rest state. Which is at rest. Let's say this frame is attached with the plane sheet, because plane sheet is at rest here. So this is S frame. And we also are going to consider another frame that is called S prime frame. S prime frame, let's say, attached with the particle. That means S prime frame will move with a velocity v equals to beta c parallel to the x-axis with respect to the S frame. So here S prime frame is the moving frame, and it moves with a velocity v equals to beta c and in positive x direction with respect to S frame. Okay, so now from the figure we can say that the distance between this point to this point is L. This point to this point is L. So in order to calculate the dipole oscillations, so first what we have to do, we have to calculate the time period of the oscillation. So you can see here at this point, when charge particle at this position, that time dipole is maximum, and then it will goes to reduce almost zero at this position, and again it will be maximum at this position. So from here to here, this will complete one oscillations of the dipole. So once we can calculate how much time particle will take to travel from this point to this point, and that will be the actual time period of the oscillation in S frame. In S frame. So let me write that first. So the time period of dipole oscillation in S frame is t is equals to L divided by velocity. L divided by velocity. So L and then velocity v is equals to is given in questions beta c. So this will be the time period. Now this actually dipole is oscillating in S prime frame, because charge is rest at S frame. S prime frame. So this dipole is actually oscillating in S prime frame. That's been phenomena is happening in S prime frame, and we are observing from S frame. So this time is observed from S frame. So this is not a proper time period of oscillation. So if we want to calculate the proper time period of oscillations, so that will be in S prime frame. So therefore the time period of dipole oscillation time period of dipole oscillation in S prime frame is T prime, and this is the proper time of dipole oscillation. So this can be written as, according to relativistic phenomena, this can be written as T prime is equals to T into under root of 1 minus b square by c square. So if we put it here, value of T, so it will be L divided by beta c, and then under root of, if you put the value of v is equals to beta c, so c square will going to cancel out. So what we'll get under root of 1 minus beta square. So this is the time period of oscillations of this dipole in S prime frame. So once we know the time period of the oscillations of the dipole in S prime frame, then we can write the frequency of the radiation. That is frequency of the dipole oscillations, which is going to the exactly same the radiation frequency, because radiation's frequency is exactly equal to the frequency of source, oscillations frequency of source. So in this case, the dipole is oscillating with certain frequency, so exactly the same frequency radiations it will going to emit. So therefore the frequency of the radiation in S prime frame is f prime is equals to 1 by t prime. 1 by t prime. So if we put the value of t here, so what we'll get beta c divided by L, and then under root of 1 minus beta square. So this is the frequency of the radiation in S prime frame, which is actually proper frequency. Because the dipole is actually oscillating in S prime frame. So if the observer observes this frequency from the S prime frame, he will observe the original frequency. Now if this radiation is observed by an observer from S prime frame, so according to Doppler effect, that person will observe a different frequency than this frequency, depending upon the position of the observer and the motion of the source. So according to relativistic phenomena, the relativistic Doppler effect, if the radiation source is moving in this direction, and let's say observer is in S prime observer is standing at this position, so he is going to observe the radiation along this direction, and if the angle between them is theta, velocity and the propagation directions of radiation, if this angle is theta, then according to Doppler effect, the frequency of the radiation observed observed by a observer in S frame can be written as f is equals to f prime, then under root of 1 minus v square by c square divided by 1 minus v by c into cos theta. Into cos theta, where theta is the angle between velocity of the source and the propagation directions of radiation. But in these questions it is written that the observer actually standing along the directions of velocity, directions of particle velocity. That's mean observer is not here. In this question, observer is actually standing along this line. So in this question, theta will be 0. So when theta is 0, then f that is radiation's frequency observer by this observe in S frame will be f prime into, if we put the value of v, it will be beta square into c square. C square is going to cancel out, so it will be 1 minus beta square divided by, so now theta will be 0. So if theta is 0, then it will be 1 minus v by c, and if we put the value of v beta c, c will cancel out, so it will be 1 by beta. And then if we simplify these things, what we'll get? We'll get f prime under root of 1 plus beta divided by 1 minus beta. 1 plus beta divided by 1 minus beta. So now if you put the value of f prime, so finally we'll get the frequency of the radiation that will be observed by an observer in S frame, and that will be beta c divided by L, and then under root of 1 minus beta square into under root of 1 minus beta, 1 plus beta divided by 1 minus beta. 1 plus beta divided by 1 minus beta. And then if you simplify these things, because here you can see this term is under root of 1 minus beta square. So if you factorize this term, what we'll get under root of 1 plus beta and 1 minus beta. So 1 plus beta will going to cancel out from denominator and numerator. So finally we'll get f is equals to beta c divided by L, and then 1 minus beta. 1 minus beta. So this is the frequency of the radiation that will be observed by an observer in S frame along the directions of velocity of the particle, of motion of the particle. So now in questions it is written what will be the wavelength of this radiation. Therefore the wavelength of the radiation in S frame, wavelength of the radiation in S frame, lambda will be c divided by f. So now if you put the value of f here, so what we'll get? We'll get c divided by value of f is beta c divided by L into 1 minus beta. So if we simplify this thing, so finally we'll get lambda is equals to L into 1 minus beta divided by beta. So this will be the wavelength of the radiation that will be observed by a observer from S frame. From S frame, and that has been asked in these questions. So what will be the correct option? The correct option will be option A. Correct option will be option A. So I hope you understood this problem. So thank you for watching. See you in the next video.